Good day, everybody. This is Chris with the Ancient Scholar. What I'm going to do now is I'm going to talk about some of the work that I've been doing on this other degree that I'm working on. It's a degree that is focusing on clinical toxicology, and hopefully, if I can procure finances, obviously, I'll continue working on this degree. Obviously, graduate degrees can be monetarily prohibitive, so we'll see how it goes. But anyway. What I'd like to do is just kind of take you through some of the concepts that I've been doing, and it's really interesting because I've been taking these concepts that I've learned years ago in other classes such as microbiology, anatomy, physiology, chemistry, and I'm reduxing or revisiting these concepts, and I'm actually using them in very different ways. And one of the concepts I'm going to be talking about is acid-base balance. Particularly how pH can really affect how certain things can absorb through or across membranes, and in its significance biologically and certainly toxicologically. So I want to just spend a little time kind of setting up the scenario here, and I just want to make sure that everybody's on the same page. And what I want to do is I want to talk about basically acid base, just so everybody's kind of on the same page. So when I talk about acids and bases, I'm going to generally be using a pretty standard definition called the Bronsted-Lowry definition. And the Bronsted-Lowry definition is that an acid is something that donates a proton. Okay, so if I donate a proton, we can consider that whatever it is, an acid. Protons are donated, and the way that I'll often symbolize donating a proton, it could be done in a few different ways, but you may see the term H+, the hydrogen ion, which is just a proton, right? It's a proton without its electron. That's all a hydrogen ion is. It's ionized. It's an ionized proton. Now we know that that really doesn't exist in nature, and at least in an aqueous environment, generally that proton will associate itself with a water molecule, and it will produce what's known as a hydronium ion, or H3O+. Okay, so if you imagine the water molecule here. Like so, I have the oxygen here, and I have my two hydrogens. The electronegativity of the oxygen kind of makes this partially negative, and these become partially positively charged. And when I have a substance, an acid, donate a proton, here's my proton here, that proton is going to want to associate itself with a very weak intermolecular bond with the partial negative part of the oxygen here. And that's how you produce the H3O, the hydronium ion. So these are common ways that you'll see that symbolizes as I kind of talk through and kind of set things up for you guys. And I should say that Bronsted-Lowry is not the only way we can define acids and bases, and there are actually a bit more refined ways. You may heard something called the Lewis acid and base definition, and that has to deal with electron pairs, donating and accepting electron pairs. And there's even something called the Arrhenius definition. But for what I'm going to be talking about in the next couple of videos, the Bronsted-Lowry model, if you will, is just fine. We don't have to look at other models, at least at this point. Okay, so now the next thing I want to talk about is the two basic types of acids. Now that we know what an acid is, it's something that donates protons, hydrogen ions, hydronium ions. And whenever I talk about acids and bases, I'm doing that with the preconceived notion or the assumption that we're always dealing in an aqueous environment, okay? So we're dealing in a water environment, particularly the environment within the human body or a mammalian body, or within a cell that's within an aqueous or water environment where water is the primary solvent that we're dealing with. Okay, so the two types of acids, basic types of acids, we have something called strong acids, and we have something called a weak acid. So I'll go weak here. Okay, so I have weak acids down here and strong acids up here. And let's just talk about a strong acid first. And a strong acid isn't necessarily how well it dissolves something, or if I throw something in there, will it dissolve it real quickly? Is it kind of like the movie Alien or Aliens, where you have some craziness going on? That's not quite what we mean by strong. What we mean is by how well an acid dissociates in an aqueous environment. So let's go ahead and just walk you guys through that. And what I'm going to do is I'm going to use a strong acid. I am going to have hydrochloric acid, which is a hydrogen covalently bound to chlorine. So this is hydrochloric acid. And when I put hydrochloric acid into an aqueous environment, so hydrochloric acid plus H2O, okay, there will be a chemical reaction. And that chemical reaction is going to yield the following. It is going to yield, this hydrogen is going to dissociate from the chlorine, and I'm going to have hydrogen ions being released. Okay, that's what makes hydrochloric acid an acid in the first place, is when it's put into an aqueous environment, the hydrogen disassociates from the chlorine. Okay, it goes and associates itself with water. And then, of course, the chlorine, so H plus chlorine, of course, this now becomes the chloride ion. Okay, so the molecule, the hydrochloric acid molecule, has disassociated into the hydrogen and the chlorine. And in the Bronsted-Lowry model, we often will say that this is the acid here. This is the acid part. And then this chloride over here is what's known as the conjugate base, or you may even hear the term the salt of the acid. Okay. Now, what makes hydrochloric acid a strong acid in the first place is virtually every molecule of hydrochloric acid that I put into an aqueous environment, virtually every molecule is going to disassociate. Okay, it is going to break up into a hydrogen or hydronium ion or proton and its salt. Okay, and you can see that this arrow moves from the left to the right, points in this direction, and this is to show that this chemical reaction really only moves one way, and you will hardly ever, the probability of the hydrogen and the chloride ions recombining to create the hydrochloric acid in an aqueous environment, the probability of that is very low, and that this reaction tends to move this way, and every molecule of hydrochloric acid disassociates into its acid and its conjugate base. That's what a strong acid is. Every molecule of that strong acid is going to dissociate. Hydrochloric acid just happens to be an example of a strong acid. Okay? Now, we also have what are called weak acids. And as you might guess, weak acids don't totally dissociate. There is a significant portion of that chemical that doesn't necessarily dissociate totally. And so an example of that might be carbonic acid, H2CO3. Okay, a carbonic acid. And the reaction of carbonic acid in an aqueous environment, so I'm going to assume that we're talking about H2O there as well, might look like this. It can dissociate into a hydrogen ion, and a bicarbonate ion, HCO3 negative. Okay, so here I have carbonic acid, and it has dissociated into its acid and its salt or its conjugate base bicarbonate over here. And you might say, well, this looks frighteningly similar to the strong acid, so I don't see the difference. Well, the difference is, one difference is you can see up here the arrow moves in this direction, but here the arrow moves not only to the right but to the left. And what this is telling me is that at the same time that carbonic acid is breaking down into its acid and its conjugate base, the hydrogen and the bicarbonate are able to recombine to go back to carbonic acid. So the two big differences is that this is a reversible chemical reaction to some extent, depending on how weak or strong the weak acid is, and not every single molecule of carbonic acid is dissociating into hydrogen ions, hydronium ions, protons, and bicarbonate. There's a certain amount of it that can remain in its quote-unquote original form, if you will. So those are the two big differences between a strong and a weak acid. Okay, so that's kind of the basic setup. Just some basic information about what acids are, at least how I'll define an acid for this discussion. And of course, a base is just something that can accept a proton when we talk about the Bronsted-Lowry definition, at least. And like I said, the Bronsted-Lowry definition will do just fine, or I guess I should say model, because I'm using it as a model for explaining or making some predictions, or even theory, I suppose you could say. Well, we do know that there are other theories that may need to be invoked, but again, Bronsted-Lowry works just fine for us. Okay, so that's that. That's the basic intuition behind what an acid is. And now what I think I'm going to do is I'm going to cut this off, and I'm going to pick it up in the next video, and I will get to the point of what I'm doing, but I just wanted to talk a little bit about acids and bases and just make sure that everybody's on the same page. Okay, guys, as always, thanks for hanging in there.